Okay, so for part 2 it says draw the truth tables for each of the following Boolean functions. So we just have x, not y, x and y, and so forth. So let's go through these one by one. Let's read all of these. Question 2. Truth tables. So what are truth tables? Truth tables are essentially things I've been drawing up here to the right hand side. So you have your inputs on the left hand side, whatever number of inputs, then you have your output on the right hand side. And it's simply if. So you do all the available input combinations on the left, and then you have your output, which is based off the operator you're trying to do. So your output is based on the operator, or if you like, is based on the function. Based on the function we're trying to get. So the inputs will never change. So if you have 1 input, 2 input, 3 inputs, their order, not so much the order, but their combinations will never change. And you will see that as we go through this. And we already worked out in part 1 how many output values we're going to get. So how many output values there are, and how many combinations you're going to need. So let's start with question 1, which was just simply x. So we went through this earlier. X can have zero, 1. So our input's going to be x. Output, if it's 0, it's going to be 0, and it's 1, it's going to be 1. Simple as that. That's all you need to do for a single input. You just give it x. If it's false, it's false. If it's true, it's true. It's just a simple, basic Boolean. Next question is not y. So again, even though it's not called x now, we still only have one input, y. So this time it's going to be the not of y. So we're still going to have 0, 1 here. So y can be 0, y can be 1. And for our output, when we get 0, it's going to be not of y. So we saw here we have one input, 0 got 0, 1 got 1. So here not, 0 is going to get you 1, and 1 will get you 0. So when it's false, you get true. When it's true, you get false. For the record, this is the same as you'll see other truth tables. They'll have F and T, F and T, output X. It's the same, very exactly the same thing. They just use false instead of 0 and true instead of 1, which is why they're actually called truth tables. So you have the T for true and the F for false. But we want to use binary, and we will see why later. Plus it gets you into the hang of using binary. So X and Y. So I'm going to have two inputs, and our output is going to be for the function X and Y. So, as we remember from the last video, X can be 0, Y can be 0, X can be 0, Y can be 1, X can be 1, Y can be 0, X can be 1, Y can be 1. We have two inputs, so we're going to have four possible outputs. X and Y, and we're the same as X multiplied by Y. And actually this is why we like to use the binary, because we can actually do this now. False multiplied by false. It's not really the same as 0 multiplied by 0. So 0 and 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1. That is it. Well, that's our first three questions, which we covered in the last page as well, in part 1. So not X multiplied by Y. A bit trickier now. So X and Y are our inputs. Output is not X multiplied by Y. Not X multiplied by Y. Okay. To do this, we can see X multiplied by Y is in brackets. So the actual thing to do here, again we have two inputs, we're going to have four outputs. Let's do the X multiplied by Y first. So we did that in the last one, so it's going to be 0, 0, 0, 1. And now, let's take the not of X multiplied by Y. Basically, we want the opposite of this. So we're going to do another line. We're going to do not. So it's going to be 1, 1, 1, 0. So this is the output of X and Y. And this is not of X and Y. So it's the opposite of the complement of X and Y. Or X multiplied by Y. Same thing. And that's all that answer is. 1, 1, 1, 0. Question 5 is X plus Y. Again, we have our two inputs. When you get the hang of this, it's just the same over. You just keep drawing these. 1, 0, 1, 1. So we have X plus Y. X plus Y. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. So X plus Y is the same as X or Y, as we went through in part 1. Question 6 is not X or Y. So you can actually do part 6. You can join them together. Let's do part 6 here at the same time. So this is not X or Y. Now, this not, as we saw in the last, is the same as this symbol here. We're just interchanging the symbols just to show you all the different options that you can see when you're reading about this type of things. So we have X or Y, which is 0, 1, 1, 1. So not X or Y is the opposite, or the complement. That's going to be 1, 0, 0, 0. And that's 0, that's going to be 1, 1, 0. And that's all it is. Simple as that. So not output. It's enough of that output. Now our next one is a little different. The next one says X and this little plus symbol Y. The plus is surrounded by a circle. What does this mean? Well, we know that plus is or the little v below. So we've done that, the x plus y, x or y, which is 0, 1, 1, 1. We know that gives us 0, 1, 1, 1, we have 2 different values. The circle around the plus basically means we have the or, it is exclusive or. This means we only want the or values. So when one is true and the other is false, we do not want any and values. So that means we do not want x and 1 to be true. So let's draw this out. X, y, output. Anyway, you don't have to write output, you can write the actual symbol x or y in here if you like. I just like using the word output. The inputs never change. 0, 0, 0, 1, 1, 0, 1, 1. So what's our output going to be? We only want exclusive or and not the and. So what was the or? Or was 0, 1, 1, 1. That was x or y. So let's do x exclusive or y. So 0 is still going to be 0. 0 or 0 is 0. X or y. So one of them is true and the other is false. This is what exclusive or means. One of them has to be or. That's true. 1, 1, 0. Yes. Now the 1, 1. They're both true. As we saw over here, we don't want, when x and y are true, the output is 0. We don't want that. So this is 0. So only when one of the values is true is exclusive OR work for two inputs. And not when they are all true. Now, let's say we had three inputs. Let's say if it was X exclusive OR Y exclusive OR Z. Now we're going to have a different output. So let's remove this and we'll do this over here. We have X exclusive OR Y exclusive OR Z. We have X, Y, and Z as our inputs, and we know when we have three inputs, we want to have 8 outputs. 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. I'm really happy with it. Try and keep it simple order. Okay, let's do exclusive 0. Let's see if we can follow this. So 0, 0, 0 is always going to be 0. 0, 0, 1. Well, only one of them is true and the other two are false. So that is going to be a 1. Only 0, 1, 0. Only one of them is false. 1. 0, 1, 1. So we have an AND here. We have two values. So how you actually work this out is, it's actually the same as here. You just put a 0 here. You take X, X or Y, X, actually let's try it better. Let's work from the inside out. So start at Z. So Z, X or Y. So Z is 1, Y is 1. So our output is going to be 0. Now, take this output, which is 0, and you do XOR with the last one, which is X, which is 0, XOR 0, which equals 0. That's going to be 0. And this is what we did up here as well. Wait, it's quicker. You can see 2 are false and 1 is true. You can just immediately say it's true. So here again, 0 XOR 0 is 0. 0 XOR 1 is 1. Again, you can see that 2 are true. Let's go through it like we did here. 1 XOR 0 is 1. 1 XOR 1 is 0. Again, this is, as you can see, this is going to be 0. Now, interesting. Let's take the last value. Let's leave that there for now. So x is 1, y is 1, z is 1. So x and y and z. Now you'll probably be thinking this is going to be 0. So let's find out. They're all true. Now surely if they're all true, it has to be 0. Let's actually work. Z x or y. So z is 1, y is 1, and they're both 1. Its output is 0. So our output x or x. So 0 x or what is x? It's 1. It's actually 1. Our answer is actually 1 here. So this is why you work it out from inside out. So you do z, x or y, get your value, and you x or that value, and the output of this against the next value. And however many inputs you have, you just keep doing. And there is your final output for tree 0, 1, 1, 0, 1, 0, 0, 1. And can anyone notice the pattern? You'll notice that these 4 characters are the opposite of these 4 characters. And that's where is question 7, exclusive OR. We'll go back to the 2. We only care about when one of them is true. When you're dealing with 2, when you're dealing with 3, you just XOR all the inputs until you get 0 or 1. Now, next question, XOR complement. Let me actually get that back. Okay. So XOR complement is also known as exclusive NOR. This is known as XOR, exclusive OR, that's what the symbol means. This is exclusive NOR. So X exclusive NOR. Maybe we use the complement. This is just simply the opposite of exclusive OR. So 1, 0, 0, 1. Which you might remember when we did the tree inputs. It was actually XOR and exclusive NOR. It's just interesting to see that pattern. And that's question 7 and question 8. Now, our next question is implies. Question 9. Yes. So X implies Y. This basically means if X is true, Y is true. Or let me rephrase that. If X is true, Q must also be true to get a positive output. If X is false, then you will always get a true output because, as anyone knows from doing proofs in mathematics, and your math teachers, you can prove any hypothesis if your hypothesis to start off with is false. So again, we have 2 inputs, 0, 0, 0, 1, 1, 0, 1, 1. And our output is going to be X implies Y. So let me write this out. If x is true, y must also be true to get a positive output. If it's false, then all output will be true. Because essentially you can prove anything with a false hypothesis. So x0, y0, so when x is false, we already said, all output will be true. X is 0, so again we're going to get true. So let's start here. Here's where it's actually interesting. So when x is true, it says here y must also be true. But here x is true and y is 0. So we're actually going to get 0. So x is 1, y is 1. So when x is true, y must also be true. That is the case. So 1. This is what x implies y, x, that dash arrow y means. This is our output, 1, 1, 0. So just remember, if x is true, y must also be true. You get a positive output. If x is false, all outputs will be true because you can prove anything from a false hypothesis. Now, I believe the next question is the double implies. Yes. So, that's good. Let's put an arrow as well going the other direction to x. So x implies y and y implies x. What does this mean? This means if x is true, y must also be true. And if y is true, x must also be true. If x and y are false, you're going to get true. Let's go through with x, y, output. 0, 0, 0, 1, 1, 0, 1, 1. So x implies y, we're starting with false, we're going to get true. And y implies x, again we're starting with a false. So it's going to be true. So if they're both false, we're going to get true. Let's try the next one. X implies y. So x is false, y is true. So you're going to get a true, which would have been 1. However, we have implies going the other direction. So true implies false. It says here if y is true, x must also be true. But this is not 1. This is 0. So x implies y is true, but y implies x is false. So it is false. Same here, x implies y, that's immediately false, so 0. And last one, x implies y, true, y implies x, true. 0, 0. And our final question in this is x and not y and z. So we have 3 opens. was x and not y and z. We have 3 inputs. Oh. Now I'm going to show you a trick for creating these. We used to do 0, 0, 0, 0, 0, 1, etc. What actually there is there's a pattern. So you take the inside variable and you just go 0, 1, 0, 1, 0, 1, 0, 1, or how many values there are. And let's just say this is a positive y for now. This is x, y, z. This would be 0, 0, 1, 1, 0, 0, 1, 1. And for the third one, it's going to be 0, 0, 0, 0, 1, 1, 1. That's just a quick way of creating the binary tables. The inside variable will always be 0, 1, 0, 1, 0, 1. The next one will always be 0, 0, 1, 1, 0, 0, 1, 1 for many inputs are available. And the one after that will be x 0, 0, 0, 1, 1, 1. And if you had another variable here, or you'll have 8 zeros and then 8 ones, and then just continue these. And it goes up in power of 2. So if you have another one, it'll be 16 zeros, 16 ones, etc., etc. And you'll notice that 0, 0, 0, this actually doesn't change the values of y and z. So if you just do the table of y and z, you'll get an output table. Putting a 0 in front of it won't change any of these values. So the first half of the table is essentially just y and z. The second half of the table, where x changes into a 1, it will change the values. It's just that's another way of looking at it. Now, for our table, we have x and not y and z. So these values will actually go the other way around. Instead of 0, 0, 1, 1, you'll have 1, 1, 0, 0, 1, 1, 0, 0. Because it is not y, it is the opposite of y. So it's now the end of all these. Yep, we have 0, 0, 0, 0, 1, 0. So only when x is true, not y is true, and z is true, we get an output of 1. And you can see that this is here. 1, 1, 1, 1. 1. The ends are always the easiest ones to make. Because once you see a 0, you're going to get a 0. That's why you gotta remember with an end. If any of the inputs is 0, the output is 0. And with an OR, if it's x or y, if any of the inputs are 1, the output will be 1. And that is essentially part 2. In the next section, we will show you how to turn these truth tables into decision trees. And from there, to binary decision trees.